Example 7. Let A equal the area of a circle and let R equal the radius of the same circle. Is A proportional to R squared, the circle's diameter, or none of the above? You may recall from your previous experiences working with circles that the area of a circle can be shown to be equal to pi times the square of its radius. That is, A equals pi r squared. Recall, pi is the constant we get when we take the circumference of any circle and divide it by its diameter. Moreover, since the value of A and the value of r squared can change, we can think of them as variable quantities. So area equals pi r squared is an equation of the form variable equals constant times another variable. This should look familiar to you. By the definition of proportionality, variable quantity A is proportional to variable quantity B when there exists a non-zero constant C such that A equals C times B. In our example, we have A equals pi r squared. This means A and r squared are proportional, and pi, a number that is approximately equal to 3.14, is our constant of proportionality. So once again, the correct answer is that A is proportional to r squared. Part B. If the radius of a circle is doubled, what happens to the area? Let's start with the formula that relates the radius of the circle to its area. We have A equals pi r squared. Now let's double the radius. Be careful with this. We want to double just the radius, not the square of the radius. That is, we want to multiply radius by 2 instead of multiplying the square of the radius by 2. The difference may be subtle, but it will have an effect on what happens to the area, so it's important to do it correctly. We can simplify this formula by squaring 2r. To do that, we square both 2 and r. 2 squared, of course, is 2 times 2, or 4. This gives us pi times 4r squared, which is the same as 4 pi r squared. Notice that the new area is 4 times the area of the original circle. This means doubling the radius results in quadrupling the area. One application of this is deciding what size pizza to buy. The size of a pizza is normally given by its diameter. Suppose a small pizza was 8 inches long and cost $8. A large pizza was double the diameter, but also double the price. Since the radius is half the diameter, notice that the large pizza also has twice the radius of the small pizza. From our work in this example, we know that the area of the large pizza is quadruple the area of the smaller pizza. So even though the large pizza is double the price, it is a better deal because you're getting quadruple the pizza. In general, large pizzas are often priced marginally higher than small pizzas. So it's almost always a better deal to buy the larger pizza, as long as you have plenty of friends to help you eat it or a refrigerator to store it in. Example 8. Suppose we have several boxes of different sizes, each of which is the shape of a cube. Is the volume of a box proportional to A, the length of one side of the box, B, the square of the length of one side of the box, C, the cube of the length of one side of the box, or D, none of the above? Since we are interested in the relationship between volume and the length of one side of the box, let's let V equal the volume of the box and X equal the length of one side of the box. From your previous experience in math, you might recall that the volume of a box equals its length times its width times its height. Since we are working with a cube, the length, the width, and the height are all the same. And we've given them the variable name x. This means volume equals x times x times x, or x cubed. To show volume is proportional to another variable, we want to find an equation of the form volume equals constant times another variable. So let's rewrite this. V equals 1 times x cubed. And note that because v and x cubed can change value, they are considered variable quantities. Well, 1 is our constant of proportionality. So, by the definition of proportionality, the volume of a box is proportional to the cube of the length of one side of the box, or x cubed. Part B. One of our boxes has sides that are twice as long as those of another box. How much more does the larger box hold than the smaller box? Let's start with our equation that gives the relationship between the length of one side of the box and its volume. Since one of our boxes has sides that are twice as long as those of another box, let's double the length of one side of the box and find out what effect that has on its volume. Once again, be careful just to double the length of the box and not the length of the cube of the box. That is, we don't want to simply multiply x cubed by 2. We want to multiply x, the length of one side of the box, by 2. Now, when we cube 2x, we get 2x times 2x times 2x. We can also write this 2 times 2 times 2 times x times x times x, or 2 cubed times x cubed. Since 2 cubed is 2 times 2 times 2, or 8, the volume of the box that is twice as long as the other box can be described as 8x cubed. Since the volume of the smaller box was just x cubed, and the volume of the larger box is 8x cubed, we can see that doubling the length of one side of the box has the effect of multiplying the volume of the box by 8. That is, the larger box has 8 times the volume of the smaller box, and therefore can hold 8 times the material. You could find applications of this example at the post office. Perhaps you want to ship a box full of jelly beans to your good friend, and you want to know if paying the additional cost to ship the larger box is worth your money. Now you know that if you double the length of a cube-shaped box, you can fit 8 times the jelly beans. Example 9. Is the surface area of a cube-shaped box proportional to A, the length of one side of the box, B, the square of the length of one side of the box, or C, the cube of the length of one side of the box? Let S equal the surface area and X equal the length of one side of the box. To find the surface area, we need to add up the areas of each of the faces of the cube. And since the length, width, and height of a cube are all equal, each of the faces has an area of x times x, or x squared. This means the surface area is equal to x squared plus 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 x squared, or 6x squared. Since s and x squared can change in value, they can be thought of as variable quantities, while 6 is our constant of proportionality. That is, the surface area of a cube-shaped box is proportional to the square of the length of the box. Part B. The cost of wrapping paper for a box is proportional to the surface area. What happens to the cost of wrapping paper if the sides of the cube are doubled in length? Note, the cost of wrapping paper is determined by the amount of wrapping paper needed, which is determined by the surface area of the box. This means we need to find out what effect doubling the length of a cubic box has on its surface area. We will start with the equation that gives the relationship between the length of the box and its surface area. S equals 6x squared. Now we will double the length of the box by multiplying x by 2. We get S equals 6 times the quantity of 2x squared. Note, we are interested in doubling the length of the box, not doubling the square of the length of the box. So we want to make sure we multiply x by 2 and not x squared by 2. The quantity 2x squared is 2x times 2x, which equals 4x squared. We can rearrange the right side of the equation so that part of it matches the original equation. We get S equals 4 times 6x squared. Since originally the surface area equaled 6x squared, we can see that doubling the side length resulted in multiplying the surface area by 4. That is, the new surface area is 4 times the original surface area. And since the cost of wrapping paper is determined by the surface area of the box, the cost of wrapping paper quadrupled as well. In summary, variable quantity A is proportional to variable quantity B if there exists a constant C such that A equals C times B. We call C the constant of proportionality. If A is proportional to B, multiplying B by K results in multiplying A by K. In particular, if B doubles, A must double as well. Next, if variable quantity A is proportional to variable quantity B squared, then there exists a constant C such that A equals C times B squared. This time, multiplying B by K results in multiplying A by K squared. We saw this in example 7. When we doubled the radius, the area of the circle quadrupled. Finally, if variable quantity A is proportional to variable quantity B cubed, then there exists a constant C such that A equals C times B cubed. In this case, multiplying B by K results in multiplying A by K cubed. We notice this in example 8. In that example, we multiplied the length of a box by 2, and the volume was multiplied by 2 cubed, or 8. Note that an alternative definition of proportionality requires the ratio of two variable quantities to be constant. We call this constant the constant of proportionality. In geometry, one important application of proportionality involves similar triangles. Two triangles are similar if all corresponding angles have the same measure. The most important feature of similar triangles is that the ratio of corresponding sides are the same.